In this video, I'm going to go over the system architecture schematics for the OpenVentilator Spartan Model Mk1. I'm also going to take a look inside of this valve pack and see how it's doing what it's doing. All of this information should be already on the GitHub in the documentation of the OpenVentilator Spartan Model Mk1 5 to 20. But if you want to see it explained in video, that's what this is for. Okay, let's get going. So this is a system architecture diagram of the ventilator. I'm going to go through its parts and pieces and we can see exactly how it's doing what it's doing. The first part that I want to go over is the electronics, and they are here. Let's zoom in. Okay. So the electronics consists of a power supply, an optional car battery backup, a diode ladder, and we'll see the function of that later, two 12-position switches, a motor. This is a car windshield wiper motor. I'm using a Bosch out of a Jetta. And then a limit switch and a relay. And this relay can be replaced with a bigger limit switch, and we'll look at that later. Okay, so First, you have a ATX power supply out of a computer, and that will provide 12 volts out and also 5 volts out. I'm using 5 volts to power the relay and also to power the switch, which toggles the relay on the power side between these two limit switches. You can have an optional battery backup in the system here. But this is not necessary for the system to function. It's only necessary if the power goes out. Here on the 12-volt line, we have 14 diodes. They're not all pictured here in a ladder. They're in series 1, 2, 3, 4, 5, all the way down to 14. And they drop the voltage by 0.7 volts between each diode. So here we have 12 volts, and here we have 11.3 volts, and here, so on and so forth. These 12-position switches in their center tap are connected to the relay, and each one of the positions connects their line to the relay to a different point in the diode ladder. So by changing the position of each one of these switches, we change the voltage provided to either side of this relay. One is for inspiratory speed and one is for expiratory speed, and these will change the voltages on the motor during each one of the inspiratory and expiratory cycles. The motor turns this crank disc. The outside of the crank disc has this semicircular cam. It's 180 degrees, so that when the crank is moving down and pushing the bellows over here, we're on the inhale cycle for the patient, and the limit switch is open. On the exhale cycle, when this crank comes around, the cam comes into contact with this limit switch, closing the switch and changing the relay from inhale cycle to exhale cycle. The center tap of the relay goes out to power the motor here. So when this crank disc turns around and around for half the cycle, we give inspiratory voltage to the motor, and for the other half of the cycle we give expiratory voltage to the motor. And again, this whole system can be replaced with a beefier limit switch that can handle the amperage being pulled to the motor, and I think that's a better design. They're using that in Brazil right now. I just don't have a limit switch that can handle the current pulled by the motor. The advantage of that is you don't need a 5-volt line to control the relay, and if you don't need that 5-volt line to control the relay, if the power goes out, then this backup, this battery backup over here can function perfectly with everything. Right now, in this design, if the power dies, you lose 5 volts to the relay and you only have 1 speed over here. Now you could add a secondary power supply or a voltage converter to go from 12 volts down to 5 volts and power the relay that way, which would work on battery backup if you have to use a relay. But even better is just to use a limit switch that has 2 positions and have that do the work of the relay. Okay, so that's the very simple electronics in the ventilator. There's no digital components besides this power supply. And yeah, it's very simple and anyone can make it. Now let's take a look at the pneumatics. Zoom out here. Okay, so the pneumatics are also fairly simple. We have this crank moving around which pushes a piston up and down, which compresses a bellows, pushing air into the system or sucking air into the bellows. So over here we have an oxygen supply, a flow regulator, and a Venturi valve. None of these pieces are included in the scope of the ventilator that we built. Oxygen tank and flow regulator are commonly available parts. If you have oxygen, you probably have a flow regulator. This Venturi valve, there are a lot of open source and crowdsourced projects 3D printing these or injection molding these, and these are also available medically. We take this as a given in our project and have tried to not reduplicate the efforts of others. We plan to just use one of these guys from a different project. Over here we have a intake air module. What this has is this basically a 4-inch piece of PVC pipe with a fitting down here. On the top there's a HEPA filter, or the best filtration material you can get, which is held in place by a rubber band, and sealed into the piece of tubing or pipe is a UVC lamp that has been filtered to not create ozone. It's extremely important that you don't create ozone and pump that into a patient. It has really terrible effects on humans, but they sell UVC sterilization lamps that do not emit ozone, and that's what we would like to use here. Okay, so we have an air supply coming into the Venturi mixer. We have oxygen coming into Venturi mixer. Now, there are 1, 2, 3, 4, 5, 6 valves in this system. All of these are within the compound valve block, which we'll take a look at in a minute, but for functional schematic or system architecture purposes, we've broken them all out individually so we can take a look at their function. On the way in, let's ignore the autonomic inhale bypass for now. That's this leg right here. But on the way in, we have a check valve to the pump, which allows on the inhale cycle for the pump to suck air in from the Venturi mixer, which sucks oxygen and air from this tank in the intake module. And then we have a check valve out so that when the pump is sucking in, it closes this check valve. In my symbology, these check valves, the arrow is direction of flow. So air can come through this way and it can come through this way, but it cannot be sucked from the patient back into the pump, right? We don't want to recirculate the air in and out of a patient. That would lead to too much CO2 buildup. Okay, so the pump, when it compresses, it can push air down this leg. Again, when the pump is compressing, this valve is closed due to pressure on this side of this check valve, and it pushes air or mixed air through this check valve and down to the patient. Over here we have a Y tube or a T, a heat and moisture exchanger, which maintains moisture and heat on the patient side of this circuit. That's a commonly available and inexpensive medical part. And then a nasal cannula, intubation setup or mask, and then finally the patient. As well, on the expiratory leg, we have over here a check valve going to the overpressure system, which is just a tube sitting in a 4-inch piece of PVC filled with water. So the tube is adjustable in terms of how deep the end of the tube is in the column of water. So this tube can move up and down. And the end of this tube determines the hydrostatic back pressure on the tube, and thus how much pressure needs to be applied on this circuit for gas to bubble out. And what this tube does is creates an overpressure maximum setting, so that when an overpressure setting is reached, no more air is pumped into the patient, but instead it releases through this overpressure. During normal operation of the machine, if the machine is functioning properly, this should never bubble, but this is a safety blow-off valve. Again, once gas escapes through the liquid in this overpressure and PEEP chamber, this is a sealed chamber with one port that heads over here to an exhaust module, which works exactly the same as this intake module over here. Again, has a UVC light for sterilization, the best filtration material you can get, either a HEPA filter or some sort of carbon filter, and a rubber band that keeps it in place so that we don't exhaust aerosolized virus into the environment. Okay, now on the expiratory leg, I'm going to zoom in a little bit here. On the expiratory leg, we have this pressure gate valve, which I think is a pretty clever little thing. This does the work of a lot of digital electronics. In a traditional ventilator, you would use something like a pressure sensor or some sort of cycle sensor. You would use a microcontroller and a solenoid valve to achieve what this valve does. So basically there's two chambers down here. One chamber is connected to the patient's expiratory leg. The other chamber is connected to the PEEP system. We'll get to the PEEP system in a second. And then this top chamber is connected directly to the pump. Now, the pump pressure is reflected in this top chamber. However, there's no flow from the pump here. There's no exit port in this chamber. Between these three chambers, there's a flexible silicone membrane in the valve pack that can move up or down, thusly closing or exposing the patient expiratory chamber to the PEEP chamber. And we'll take a look at how that works specifically later. Then the PEEP chamber is connected again through a check valve for safety. And slide this. Then that check valve leads to another adjustable height tube in this liquid tank. The PEEP tube can be set at a different height to change the hydrostatic pressure at the bottom of the PEEP tube, which will maintain a back pressure or a positive end expiratory pressure during the exhale cycle on the patient. Let's take a look again. This guy. So what's happening here is during the inhale cycle, the pump is compressing, pushing high pressure onto the top of this membrane, and actually an equal pressure through this tube and back into the patient pressure chamber. However, that's always going to be a higher pressure than maintained in the PEEP valve pressure chamber, thusly sucking this membrane down and sealing the PEEP pressure chamber and PEEP exhaust. So when we push high pressure from the bellows into the patient, it cannot be blown out through the low pressure PEEP exhaust system. Then in the exhale cycle, we want to open this chamber to allow the patient to exhale through the PEEP system. So what happens is during the exhale cycle, the bellows expands, it moves up creating vacuum or a low pressure in this area, sucking this membrane up. As well, there is now a higher pressure from the patient pushing this membrane up from the patient pressure chamber, thus exposing the patient pressure chamber to the PEEP valve chamber and allowing the patient to exhale through the patient pressure and PEEP chamber, through the check valve, and ultimately into the PEEP system up until their pressure matches the hydrostatic pressure at the end of this tube. Then again, the exhaust, once it bubbles through this fluid, be it water or bleach or hydrogen peroxide, this fluid cannot be sucked back towards the patient because of these two check valves, but it will sterilize to some extent the aerosolized virus in the bubbles coming out of the PEEP. And then this is a sealed chamber with a port that moves down here to the exhaust module, which again has the UVC bulb and the filter. So this leg of the system, we call it the autonomic inhale bypass. It's questionable whether this is absolutely necessary, but what this is for is to allow the patient, if there's some sort of autonomic inhale during the exhale cycle, to continue to breathe around the pump. So what happens is during the exhale cycle, right, while the patient is exhaling, the bellows is inhaling, right, and it's pulling a vacuum on this check valve, thusly closing it to the patient, right. So if the patient were to inhale, this chamber would be sucked closed, and this check valve would also be sucked closed, as with this, and the patient would have nowhere to breathe from. So what we've done is add another check valve here that goes directly to the Venturi mixer to allow that patient to inhale through this leg of the system. Now, at slower speeds, the patient maybe could create enough suction to open this check valve such that while the pump is inhaling, it's inhaling through here, but this check valve would still open, allowing the patient to inhale through this valve. However, if this is inhaling quickly, the bellows is inhaling quickly for that matter, and the patient is only weakly inhaling, we are unsure that this check valve would open, and so that's why this inspiratory bypass leg is in the system. Okay, so now what I want to do is take a look at a schematic of this valve. We have a CAD cross-section of it, so we can take a little bit better look at how it works. And then we'll take a look at this compound valve block that includes all of these valves here in one piece. Okay, so now this is a cross-section of just the portion of the compound valve block that includes the pressure gate valve. Let's take a look at it in steady state up close. So what we have right here is this chamber, this upper chamber, is connected to the bellows. Again, it has no flow through it, but it reflects the pressure inside the bellows. So during the inhale cycle, this is a high pressure inside of this chamber, and during the exhale cycle, this is a low pressure. Then over here we have patient pressure, and this is connected to the T or Y tube at the patient. And over here we have a chamber that's connected to the PEEP system. First the check valve and then the PEEP tube within the fluid tank. So then we have these two cycles. During the inhale cycle, the pump is pushing high pressure, which pushes this membrane down. The patient pressure is actually equal, but the PEEP pressure is always lower than the pump pressure, thus sucking this membrane to close this port, and thusly sealing the PEEP system from the patient during the inhale cycle. Then in the exhale cycle, what we have is the pump pressure is low, sucking this membrane up. The patient is exhaling until PEEP is achieved, right? Always higher than PEEP pressure. And so this membrane is blown up deflected up, and air can flow under the membrane from the patient pressure to the PEEP chamber, and then out through the PEEP system. And so I think it's interesting that usually when we teach electrical engineering, we use fluid analogies, like a resistor is a stricture through a pipe, or a transistor is some sort of a valve. I'm going to use an electrical analogy to explain this, which is I think of this much like a transistor or a MOSFET, where this is the gate up here, right, where you can apply voltage but there's no flow. And that applied voltage will either expose, the collector and the emitter to each other, or not. And I just thought that was an interesting little thing. And in fact, the cross-section of the actual device, which this is, looks a whole lot to me like the SEM images of a transistor or a MOSFET. Just something interesting I thought I would point out. Now I want to take a look at the physical structure of the valve block. This is a compound valve. It has all of the 6 valves shown in the system architecture picture here. But this is their actual physical layout in the CAD files. I've made an exploded semi-isometric view so that we can see each one of the layers. Before we get started with how it works, I just want to point out that this is a faceplate, this is a seal, these are the ports that go to tubing, this is a mounting plate, this is a seal, and this is a mounting plate. And so for all practical purposes, these are not part of the valve system, and so we can kind of ignore them. Likewise, this is a seal and this is a backing plate, and these don't have really anything to do with the function of the valve other than sealing the block. So really where the action happens is this plate, this membrane, this plate, and this membrane. So we're going to look at this valve block assembly in different cycles and see how the flow and pressures pass through this valve block during the function of the machine. Okay, so now let's take a look at the valve block in the first inhale cycle. One thing I wanted to point out is in purple here, we have silicon membranes. That's there, here, 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 and here. It's a little hard to see. And then red lines indicate pressure but no flow. So there's a lot of, pressures closing or opening check valves that don't actually have flowing gas through them. Okay, so during the inhale cycle, the pump is compressing and pushing air through from the pump port. Again, these are just mounting blocks for these nozzles, so we can kind of ignore them. But the pump is pushing air in through these ports and into the top of the pressure gate valve. That pressure then pushes down on this membrane, helping to seal this line between the patient pressure chamber and the PEEP chamber. I'm going to zoom in a little bit over here so we can see a little bit better. Again, this membrane is being pushed in this direction by the pump pressure, sealing the line, this gate, between the patient pressure and the PEEP chambers. Okay, so the high pressure in this chamber here blows out through this port here and this check valve. You can see that there's a check valve support in this smaller hole and no support in this larger hole in this chamber. And so air can flow through here, up here, and then out. Let's zoom out a little bit. Out to the patient. Now, here we have a from patient line that enters through this nozzle. If and only if that pressure is higher than the hydrostatic pressure exerted on the bottom of the overpressure tube in the liquid tank, this this gas can flow through the patient pressure tube. Again, cannot exit the PEEP, but can exit through this check valve and through the two overpressure system. You'll notice that this is a dotted line here, and that's because under normal circumstances, unless, say, the patient coughs or something malfunctions with the pump so that it's producing more pressure than the set overpressure in the liquid chamber, there will be no flow from the patient or out to the overpressure system during the inhale cycle. Now let's take a look at the exhale cycle. Okay, so now the patient is exhaling. They have the peak pump pressure inside their lungs at the beginning of the exhale cycle. That is pushed through this port into the patient pressure chamber in the gate valve. Again, over here we have a vacuum or low pressure pulling this membrane up into this chamber and exposing the patient pressure chamber to the PEEP chamber, right? So air can flow around from the patient pressure into the PEEP pressure. So let's take a look at that. So air can flow through here. Then down at the bottom of this chamber, we have the check valve leading to the PEEP system. That's this flap. And again, there's some support in this hole so that the flap can't be sucked into this hole, but it's being blown out this way through an exposed hole. And then the flow exits through this PEEP port right here to the PEEP. Okay. So the last thing that I want to look at in this diagram is an autonomic inhale, something like a yawn, during the exhale cycle. So the pump is doing the same thing. It's sucking air through this valve, through this chamber, again from the air gas in port. But the patient creates a suction or two patient port, which, let's see, enters this chamber. Pulls this check valve up, opens this port to this chamber. This chamber is then connected directly through these holes to the air in or O2 mix. So the patient can breathe around this entire system while the pump is inhaling and the patient should be exhaling. One more thing that I wanted to mention is while I use this diagram to explain the cycle times, and we have cycle diagrams of the valve block, in the documentation there are also cycle diagrams in the system architecture. This is cycle 1, this is cycle 2, this is cycle 2A, and each one of these explains the flow of gas and pressure through this system that corresponds to the flow of gas and pressure through the physical diagram. As well, there are electrical flow diagrams as well corresponding to cycle 1, 2, and 2A in the documentation. So if you're really curious and want to match this guy to this guy, take a look at the OpenVentilator Spartan Model Mk1 version 5.2.20 in the GitHub, and that will have all of these images. Thanks. Okay, so the next thing I want to do is take a look at the actual valve, disassemble it, and take a look at what it's doing in reality. Okay, so here is the valve block. It has ports for the pump, the gas in from the Venturi mixer, to and from the patient. These go to the Y tube right before the HME and the nasal cannula intubation set or mask, and then to the patient. And this goes to the PEEP port on the liquid tank, and this goes to the overpressure port on the liquid tank. So you can see it's a series of flat cut, laser cut acrylic, along with some silicon flat laser cut pieces. And it's got a bunch of M3 screws and nuts on the backside holding this whole piece together. Interestingly enough, as it turns out, we had planned to bond some of these acrylic layers that are two different acrylic layers together that do not have a seal between them, but we found that it seals perfectly just with a little bit of pressure and tension from these screws, and some of these layers don't need a gasket between them. Some of the layers certainly do, because those form gaskets and membranes and check valves within the system. So let's disassemble this. Okay, so now I've removed all of the nuts from the gasket bolts. Let's shake the bolts out. Okay, so now let's take a look at some of the layers. These are all 3mm cut pieces of acrylic. Some are double layers to get 6mm because I did not have any 6mm in the scrap that I cut. However, you can certainly cut stacks of 3mm acrylic or single 6mm acrylic pieces. I will caution that if you use all 6mm acrylic pieces for this compound valve block, you will need some very long M3 hex screws, which you can come by, but they're a little bit harder to than these are, I think, 50mm. Okay. So the first thing we have, oops, they're a little stuck. Break them apart. Okay. So the first thing we have is the faceplate. This just holds these ports in place. I'm going to flip it over here. The next thing is we have a silicon gasket. All of these silicon gaskets are 0.5mm thick silicon. They can be easily sterilized. Yeah, let's try and keep these in the same direction. Nope, like that. Okay. Then we have these ports here. One thing to note is that sometimes 3mm acrylic is 2.5mm or 3.2mm, and so in the source files, this thickness here is adjustable so that your ports can match the thickness of these plates and be solidly sealed within the valve block, but also not force them apart. So that's one number that can be adjusted on the 3D printer files, or these could also be cut from a piece of like a nylon hose fitting or injection molded in a production situation. So I'm going to take these ports out. Okay, so the next thing we have is 6mm of plates that just space where the ports go. Then we have our first seal. These seal the bottom of the ports. Again, this is just a gasket, not a membrane. Now we start getting to the interesting parts of what goes on in the valve. So we have this top plate of the valve, excluding these port mounting plates. And then here we have our first set of valves within the compound valve body. So these flaps are cut silicone that those two form check valves that can exit. Let's see, those are for the PEEP and the overpressure setting. So this is PEEP, this is overpressure. And so gas can flow out this way, but it cannot flow in this way. So if we remove this guy, we can see here we have these little supports that prevent the check valve from being sucked in. As well, the diameter of these holes or these valve flaps is larger than this diameter in the back of the check valve port and smaller than this diameter here in the front of the check valve port. So these valve pieces can move in this direction, but they cannot move in this direction. So for example, let's do this. Let's see if I can get my face in here. If these are aligned, you can blow through but not suck through one of these ports. Okay, so that's how those valves work. So in this plate, we have the 2 ports for the overpressure and the PEEP. The PEEP ports. These are the backing for the. Let's see if we can see the backing for the check valves here, and then here we have another channel and check valve. Let's get to something more interesting. Here we have the PEEP chamber and the overpressure and patient chamber. Again, this leads out to the overpressure, this leads out to the PEEP, and this is coming in from the patient. On this side of the chambers, they are backed so that air cannot pass from here to here, here to here, behind this acrylic. However, underneath it, which is backwards from the way we presented it in the diagram, but underneath it there's a flexible membrane here. Let's just put these aside here. This flexible membrane can be pushed this way to expose the patient to the PEEP like this. Let's see, a screw. You can see that even when everything's together, you can put an object under there. Let's zoom in. Well, here we can see you can slip a screw underneath that side. Okay, and so then we have the rest of this check valve here, a through port, the backing of these check valves. This is the autonomic inhale bypass. This is the autonomic inhale bypass chamber, and I believe this is the pump chamber. Okay, so if we remove these guys, we have, again, 1, 2, 3 check valves on this layer, and then this portion here is the gate or the membrane inside of the pressure gate valve. Then we have these pieces of acrylic. First, a top backing plate here. Let's take a look at this white one because it's a little easier to see. Again, this is in from the pump over here, and then this is the chamber that forms the gate of the pressure gate valve. This will either push or pull a membrane sealing the patient and PEEP chambers within the pump. And then last but not least, we have one more seal and the backing plate. That's it. So I'm going to put this together. I'll do it in high speed. And over here I've made some registration marks just so that, just so that I can assemble the valve quickly in the correct order. A Sharpie is an indispensable engineering tool. So when I put this together, I want to use just finger tight nuts to begin with, and then I'm going to tighten them up a little bit more in a star pattern to keep the gaskets flat, much like an engine head. They don't need very much pressure, but a little bit will seal the valve block. Okay, so once you have all of the nuts and bolts on loosely, you're going to want to just tighten them all up. I like to use an electric screwdriver, but only use my fingers on the back side so that I can't over tighten these. There you have it, a completed valve block. You can take it apart and sterilize it pretty easily and reassemble it in a matter of minutes. Now let's go strap it to the machine and see it in action. Okay, so now that we've assembled the valve block, let's hook it to the machine. Alright, so the connections are fairly simple. This guy comes from the pump over here. So that goes to pump. This goes to the PEEP. This goes to the overpressure. This guy is from patient. And this guy is to patient. One thing I will say about using vinyl hoses is they are prone to kinking. In a professional ventilator, these would be corrugated tubes. If you can get your hands on corrugated tubes, that would be way better than vinyl tubing because it doesn't have the risk of kinking and cutting off flow. So once you have the valve block assembled, there are these two screws which just mount to these two holes in the machine. It's not necessary to mount these guys into the machine for its functioning, but it's just a nice place to put it to keep it out of the way. And these don't need to be tightened down, they just sit there. Now that it's hooked up, we can turn the machine on. There you can see the valve is working. You can hear the PEEP bubbling on the exhale stroke, so if we listen carefully, bubble, 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 bubble. Bubble, 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 bubble. And so you can see that it's bubbling only while the pump is inhaling and the patient is exhaling, and that's going out through the PEEP tube over there. Okay, thanks very much for watching. I hope you enjoyed this video, and some people can use the information either to design better systems or improve this system, or it will inspire somebody to buy us a test lung or build one and hook it up to their own test lung. Thanks very much. You have a nice day.